So, okay, we're at the second tutorial. So yeah, as Alessandro said, we will first go back to the notebook we were looking at last time. We will try to finish that, and then there's also another one with some other exercises, and we'll see how far we can get, basically. So let's start with a brief recap. Do you remember what we did last time, more or less? Yes? No? Flat. Okay, well, I will do a recap anyway. So you remember this plot? So the aim of the game was to determine a single PDF flavor that we call T3 from a set of DIS data. In this plot here, there is a data theory comparison. So the data are everything is normalized to the data. The data are the blue line, so 1 because it's normalized with the corresponding error, and the red stars are the theory predictions computed using an input PDF set taken from the literature, and this FK table object that we introduced last time, that is basically just a linear transformation that encodes all the physics contained in the Wilson coefficients. Okay? So we see that to produce this plot, basically the only thing that you had to do was take in this object, the FK table, and multiply it, times a vector whose entries are the values of the PDF on this interpolation grid. Okay? And this was just a warm-up to understand how you can actually implement this DIS convolution when doing a fit. Okay? Then we have introduced neural networks. So in order to do a fit, we want to build a loss function. The loss function is going to be a function of the free parameters of our model, and we are using a neural network in order to parameterize the X dependence of the PDF. So we have built this object. So X is the X dependence, theta is a set of free parameters defining the network. In this code here, this thing is implemented, and at the end, so basically we can evaluate this object on the points of the interpolation grid, and then we do the convolution. So we apply the FK table to this object, and then we get a vector, which is basically containing the theory predictions for the data points, for the experimental data points, as a function of the free parameters. And then we just fit these free parameters to the data. Okay, this is what we did. In order to do this, we have built the chi-square, blah, blah, blah. And here there is the training loop. Okay, we're using gradient descent. So basically, in each iteration of this loop, we take the loss function, so the chi-square, we compute its gradient with respect to the free parameters, and then we update the free parameters following the direction towards which the gradient is pointing us. Okay, and we iterate this until we reach some kind of minimum. And in doing this, we have produced this plot. Okay, so the black line is just a reference PDF taken from the literature, just to check that we are doing something that makes sense. The green thing is our result, and so for values of X greater than 0.1, looks fine, and then it looks not so good. And again, the reason is that you remember the kinematic coverage of the data we're looking at. It's up to Q square of order, I don't remember, 100, something like that. And in X, it goes down to 0.1, but not lower than that. So you do expect to not to being able to reproduce, to get something sensible, like for lower values of X. And this is where we were last time. Okay? Good. Yeah. You can, I know, actually you have to rerun that because it has to re-download the thing and so on and so forth. So yeah, in order to do the next part, yes, you do have to rerun everything. And what is and then we also plot the chi-square as a function of the epoch, and yeah, it does make sense that it decreases. Okay, good. Now, what do we do today? So far we have not we have not said anything about uncertainties. So if I don't know exactly what you do in your research, but if you look at experimental papers from like LAC experiments, you always find a statement that everything is great, but the PDF error is huge, is the dominant one, nothing works. I mean, and then they're fine. So I mean, it's true. So the PDF, the error connected to PDF is the dominant one from the theory point of view. But yeah, so far we've just plotted a central value. So how do we define an error on this green curve? So there are different ways of doing this. Now we will discuss the Monte Carlo approach, which is, I mean, it's extremely simple. Basically, instead of fitting, so far, we've been looking at the central values of the data. So we have performed a fit on the central values of the data. In order to determine an error, you fit replicas of the data. So basically, you start, let's say your experimental data is basically a set of central values and an experimental covariance matrix. You start from here and you produce a certain number, let's say 100 replicas of the data, just sampling from a multi-Gaussian distribution, having these as a mean and covariance. Okay, so the assumption is that the data are kind of Gaussian, are distributed according to Gaussian statistics. So yeah, this is just the central values. It's not the true value of the data. Okay, so you can produce actually 100 Monte Carlo replicas, and then you produce 100 independent jobs, each one doing exactly what's on the notebook. Okay, and then what do you get? You get an ensemble of curves. Okay, and basically that ensemble represents samples from a probability distribution in the space of continuous function, if you want. So at the end of the day, what you deliver is not this green line, but it's an ensemble of lines where then are just put in a standard format and loaded on this library, which is called LHAPDF. And so basically at the end, if you're a user and you want to determine, I don't know, your cross-section for X production, so you want to determine an observable O, which is a function of some PDF, what do? Actually, you have to repeat this computation 100 times, and then you do an histogram, okay? And then you take a standard deviation or whatever, okay? And this is the way in which, so this is the way in which we propagate the experimental uncertainties of the data on the final result for PDF, and then this is the way in which, as a user, you actually compute the error associated to PDFs on the final theory prediction for your for the specific observable that you're interested in computing. Questions? Okay. So in this exercise, perform a fit on a Gaussian fluctuation of experimental data. So this exercise basically consists in attaching an uncertainty to this guy here. So what do you have to do? Well, you have to do this. So you have the experimental data, you have the experimental covariance matrix. Just produce, let's say 10, otherwise 100 we will never finish, 10 replicas, and then do 10 independent fits and plot the results. So basically in practice, what do you have to do? If you take this cell here, the first approximation, actually not the first approximation, but the exact thing is that you copy literally this thing, and then what's the only thing that you have to change in order to perform this exercise? So here we are fitting, you see, when we are defining the loss function, we are taking as input the central values of the data and the theory prediction. Now that, and okay, the inverse of the covariance matrix. The theory prediction and the inverse of the covariance matrix are be exactly the same, right? What you change is actually the central values of the data that you're taking an input. You will not be taking these, but you will be taking a Gaussian replica of it. So what you can try now to do for 10 minutes is, yeah, just paste this thing downstairs and basically put this inside another for loop. I mean, if you want to be fancy, you can do this in a fancier way. If you're still sleepy because it's early in the morning, I would suggest this. So pass this, put it in a for loop, and basically at the beginning of this for loop, at each iteration, you first generate your Gaussian replica, okay? Just Google how to generate multi-Gaussian using, and like NumPy random multi-Gaussian, I don't remember, something like that, okay? So it means that you start from a vector of 248 points, you generate another vector with the same dimension that correspond to just a Gaussian fluctuation of this guy, according to this experimental covariance matrix, and then you repeat this thing, and you do it for 5, 10 times, okay? And then you save your results, and you produce a plot like this, where instead of having just a single line, you will have 10, okay? And then we will see what we get. So, okay, let's try 10 minutes just so that you have an idea of what you have to do. And then in 10 minutes, we just look at the solutions and we go on, okay? Okay, so let's take a look at the solutions together. So, so you see here I've defined this function, fit replica. And then, okay, I'm taking as input a lot of things, even though I told you, okay, I mean, I'm not sure why I'm doing this. Like I'm taking as input twice the same information, but fine, okay. But then you see, it's basically I'm adding this noise, this flag noise, and you see if then the code in here is exactly the same as before, as in the case of a single fit. But then I'm saying if there is noise, so if this guy is true, you see the central value, which of the replicas I'm considering, which is called the Y rep. You see, it's obtained by sampling from a multi-Gaussian distribution having mean Y and covariance matrix CY, all right? And I'm using NumPy random multivariate and so on. And again, I'm casting it to float 32, otherwise it crashes, but fine. And then I'm repeating the same thing as before, but this time the central value I'm fitting is the one of the replica, okay? And then I'm returning, as before, at the end of the training, I'm returning the values of the PDF on the grid that I'm gonna use to plot it. Okay, so this is my function, and then you see I'm calling this function for 10 times, for rep in range 10. And I'm saying I'm fitting the replica number rep. I'm calling this function, which is giving me back the results on the grid to produce the plot, and also the chi-square, so that then I can plot the chi-square as before. I run this code, blah, 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 and I do the plot. And you see, I get this kind of distribution. And what do you notice here? So in the region where we do have data, the error is small, okay? So fits of different replicas will give you something which is not too different. Where we don't have data, the error blows up. And this is what you want to get, okay? So basically you want to make clear that where you don't have data, it's not that you're inventing information, okay? And so if if you have in mind some PDF plots, I mean, this is simplified examples, but in general, it's true that at small x, we don't have much experimental data. We have something from HERA and from other experiments, but yeah, from 10 to the minus 5, let's say, it starts really being extrapolation region, and so the typical plots of PDFs have this error that blows up at small x. Just like in this case, here it's a little bit extreme, meaning that here our small x is 0.1, but this is the general behavior. Then here it goes down, and then you can see that here it goes up again a little bit. And this is also because at large x, it's again a kind of extrapolation region. So in general, there are not many data there. But this is the kind of plot that you would expect to obtain. Okay, so this is the way, and then you can analyze the chi-square of each replica, and you'll see again something that decreases with the number of epoch in each case. But the point is that each replica is an independent fit. Okay. So this is the Monte Carlo approach. There are not, I mean, there are also other ways of propagating the error. So maybe I can just tell you something about that. So there are questions on this. Yeah.
So at lexical 1, apparently the shape you gave that it is not forced to go to 0.
It's not forced to go to 0, and indeed you see that you have a little spread here.
We could, as you were saying, with
yeah, exactly. We could. Yeah, but this happens at the level of the parameterization, if you want. So what happens in an MPDF is that your actual parameterization is done like this, and then you have the neural network, and so the behavior on x equal 1 is forced by this thing. Yeah, of course it would be. I've not done that because I'm lazy. I should have written more code. But yes, I mean, if you multiply times 1 minus x, you get exactly that. Another way in which you can do it is to subtract to the parameterization, to the neural network, its value in x equal 1. So for example, something that has been tried in the past is to use this kind of parameterization. So use only keep x to the power alpha. That is what gives you some control on the small x behavior. But drop the large x preprocessing in favor of this kind of form, which it works, it can work, but then it requires a lot of work just to tune everything in order to get good results from this as well. But yeah, this is something that you do at the level of the Mm-hmm. So actually, yeah, but just because this is a plot which is not done very, this is a linear scale. If you look at this in log scale, actually you would see that this is not actually the case. I can rerun, I'm not sure if no, I've not run this, so if I do this, now will be, so the point is that actually a small x, the network at some point will saturate. So if you look at this plot in log scale, you would see, has it crashed? Yes. Yeah, I should rerun everything. I can run it later and show you. Yeah, the neural network at some point they saturate, so they would go to a constant value actually. So yeah, you would see, yeah, but you're right because you're looking at this plot which is a linear scale, but if you look at the log scale, you would see that it does something like this, but then they all saturate to a constant value, more or less, which is not what you want, actually. which is why you have the small x preprocessing in real life. And actually the reason because of which saturate, I don't have an analytical argument on the top of my head, but there is an analytical argument of that. It has to do with the activations function that at some point kills everything, basically. And so you get this behavior. But it's something that you have to be aware of, because otherwise, yeah, if you just do a fit with a neural network without small x preprocessing and you don't, you're not aware of this problem, you would end up with yeah, very unphysical behavior as small x. And then people would start, I don't know, discovering new physics using your PDF and this kind of things. So, but yeah, so it's this plot that I was showing here, it's, oh, no, which is not there anymore. It's an artifact of the fact that we were looking at a linear scale plot. Other questions? So another way in which you can propagate the error is using the so-called Hessian approach. And there the idea is that, so in this case we have a lot of parameters, but if you use, because you're using a neural network, but if you use, for example, I don't know, some basis of polynomials or any other kind of simpler parameterization, you would end up dealing with, rather than 700 parameters, with maybe 30, 35 parameters. And in this case, what people do usually is basically, so they have the chi-square as a function of your parameters. Now it's a much lower dimensional space, let's say 30. And then basically, if you can think about expanding it around its minimum, okay? So you do a Taylor expansion. So basically, you would have the value of the chi-square in the minimum. Then you would have a linear term, which is going to die because we are on a minimum. And then you have the Hessian term, the second order term, right? And so basically, the idea is that you sit in the minimum and you ask for, in principle, you should, in order to, so the point is, you're in the parameter space, you're sitting in the minimum, and you want to know how much variations of the parameters from the minimum you want to allow in order to determine an error band, right? So the minimum is one value in Rn, where n is the dimensionality of your space. And then you say, okay, but then I can just walk a little bit around from the minimum in order to determine an allowed variation of the parameters so that I can determine an error. And in principle, asking for this guy to be 1 would identify a certain free for the parameter to oscillate, which correspond to 1 sigma. And this would determine the error band on your fit. Actually, what people do is not putting this equal to 1, but putting this equal to t squared with t squared equal 10 or something like this. Why? I don't know exactly. No, I really don't know. I mean, that I personally don't understand, but the net effect is that you increase your uncertainty in this way. Okay. And the claim is that you have to do this because otherwise you cannot fit properly the data. So if you just use this equal to 1, you would get an error which is just too small. And so you have to enlarge artificially your error in order to be sure that you're actually describing things well. And this thing is called the tolerance. I'm telling you because, again, it's something that you find a lot when you read the experimental papers as well. They speak about tolerance, and this is what they're referring to. In the Monte Carlo approach, actually, there is no notion of tolerance. Okay, and then people argue, oh, you should have tolerance. No, okay.
Does this second method require a lot of much more computational power?
So actually, I'm not sure because I've never actually worked with this method. Usually, I work in an MPDF that use the Monte Carlo approach. I don't think so, but I mean, but in principle, I would say less because you're dealing with way less parameters, right? Yeah, but then I mean, it's change. So I would say that in principle, you could do the minimization itself using gradient descent in the same way, and you're just having less troubles. Yeah, Alessandro.
Typically, it requires less computational power because the longest thing to do is the minimization.
Yeah.
And here you do the minimization once. Then you need to calculate the derivatives, but still you have just one result.
Yeah.
In fact, in the past, until the years 2000, all the error estimates were done only using nesting method because of limited computational power. Now, since the computational power is
Yeah.
not such an issue, is cleaner or easier, it makes sense to do 100 bits. But at the old times, it took, say, 1 day to do the fit, and there was no parallel computing or so on, so we really prefer to do one fit and then
Yeah.
the other propagation to the inverse.
Yeah, I mean, when you do Monte Carlo replicas nowadays, of course, you do everything in parallel. So, I mean, each replica run on a CPU if you want, and then you have 100 CPU, and you just do everything in one go, basically. Okay. Okay, now if we keep going, there would be an exercise concerning training validation. So maybe I would go through these together, maybe, because it would require some more coding. So I will explain you what training validation is. We look at basically at some plots, and then we start the second notebook, and at some point we will stop. Okay. I mean, I would do this because the exercise would require some more coding on your side. Maybe it's just more interesting to try to understand the concept, and then you will have the notebook, and if you will feel like that, you could just look at the notebook by yourself. Okay. So what's training validation? We've said something concerning this already last time. Basically, the idea is that say that you have a set of experimental points, and you fit all of them like to death, meaning 20K epoch until you have computational power. Most likely you will get not a good fit. And what I say by not a good fit, I mean probably you will get very small chi-square, but then we will be in a regime of overfitting. Probably you've already heard this, like overfitting. I mean, if you consider just a simple case in which you want to fit, you know, some points. I mean, this could be a reasonable answer, but then if you run your minimizer forever, you would start actually going through the single point more and more until you're just really going through the points, and in the middle you're doing crazy things, okay? So basically the concept of overfitting is that you fit for too long a limited amount of data, and you then end up basically learning the statistical fluctuation of that set of data. And it's something that you want to avoid, because all you're doing in general in this kind of problem is to determine a continuous function from a discrete set of data, and you hope that your model at the end is able to generalize to data points which have not been seen. So the PDFs that you're producing at the end will be used to compute X production, which is not in the data set which has been used to produce the PDF itself. But you don't want to bias the prediction for your unobserved data using, I mean, with the statistical fluctuation of the data which has been used in the training itself. Okay, so there is a very broad literature about this thing, and it's a very well-known problem. And like a standard way in which one can try to avoid this is by performing this training validation split. And what does it mean? It means that you take all the experimental data you have, you divide it, let's say, in a half, and half of the data will go in the training set, in the so-called training set. The other half will be the so-called validation set. And then you compute the chi-square on both these sets, but in the minimization routine. So in, where was it? So in here, this chi-square will be the training chi-square. So you minimize the training chi-square. So the description, you optimize, let's say, the description of a subset of data. And in doing this, you also compute the loss without touching it, so, on the validation set. And you monitor both of them while you go. And typically what you would expect to see is that the training loss will keep decreasing, right? Because your algorithm, that's what your algorithm is doing, is minimizing the training loss. The validation loss at the beginning should decrease as well, right? Because basically you are improving the description of a subset of data, but since the underlying PDF is the same, you do expect that also the validation data, which are not seen by the training algorithm, at first are described better and better. But at some point, the loss on the validation will start increasing, right? And that means probably that at that point, you're basically starting really fitting the statistical fluctuation of the training set. And then you know that you should stop. Okay. So in this exercise here, not this, but this, the idea was to take this simple model and just implement training validation split. Okay, so what are the steps? You divide in these two sets the data, training validation, you compute a training chi-square, you compute a validation chi-square, you perform the minimization on the training, and then you look, in the meantime, you save also the values of the validation. And so at the end, you have two vectors, one containing the training chi-square, the other containing the validation chi-square. The training chi-square will be a monotonic function, just decreasing with the number of epoch, while the validation probably will be something which at first is monotonic, but then it starts going up. And then you just look for the minimum of the validation loss. Okay, let's say that it corresponds to epoch 68. Then your best fit is going to be the one you were at epoch 68. Okay, so your best fit, the one that you trust more, is the one which minimizes not the training loss, but the validation loss. Yeah.
The result of the fit doesn't depend on the what, because I think the green set is defined randomly.
Yes.
There is no dependence on what points I can choose for the training the result of the validation.
No, of course there is, because I mean, if you choose different points, just think the loss function as a function of the free parameters. If you're changing the data, you're changing a bunch of numbers that actually you're getting a different functional form. So yes, there is a dependence, and there is, I mean, what you do in a Monte Carlo approach is that in each replica, the training validation split is randomized. So for each replica, the training set will be different. And this also ensures the fact that at the end, your final results has actually seen all the data that you have. But yeah, I mean, I'm not sure about the statistical meaning of this, but this is just what we learn when we study this stuff. But of course, yeah, there is a dependence. So for example, you could say, no, okay, I do a Monte Carlo replica where I always feed the same data in the training, and then you look at what you get. Then you do the opposite, in which you randomize, and you will see that in the second case, the error goes up a little bit, right? And usually in these kind of things, you feel better if your error is a little bit smaller than a little bit bigger, sorry, rather than a little bit smaller. Otherwise, then people will start saying that you're underestimating errors. I mean, and probably you are. Okay. So let's look. So you see here there is the same function as before, but now I'm adding. So here again I'm producing a replica. But here I'm doing this training validation split. So there is a detail here, which actually is not a detail, about which we can think for a moment. So the loss we are using is a chi-square, right? The chi-square is the shift between data and theory, the inverse of the covariance matrix, times the shift again, right? So the shift, let me call D, the experimental covariance matrix, and D transpose. So if you want to compute just, let's say, the one for the training, it means that you throw away some of the entries of this vector, right? So you cannot multiply by the same matrix as before. So you have to perform a mask of this matrix, correct? Otherwise, you're multiplying something with different dimensions. You're masking the experimental covariance matrix. So this is what is happening here. And then, okay, I mean, then you can again look at the code, but you minimize the training. Here I'm plotting again the result. And this time, what am I plotting here? It's not what I'm getting at the end of the training. Is what I'm getting by the so-called lookback. It means that I get to the end of the 500 epoch, but then I'm taking as best fit not the epoch number 500, but the epoch where the validation loss was the minimum. All right? Of course, from the plot you cannot tell, but trust me, you can check the code and see if I did the right thing. Okay? But then it's interesting actually to look at this kind of plots. So these kind of plots are, again, on the x we have the epoch, and we're plotting the training and validation loss as a function of the epoch. And you see, at first, so in blue we have training, in orange we have validation. At first they're both decreasing, and at some point the training one keeps going down, and then it stabilizes, and the validation one actually stops going down. There is some kind of minimum, and then either it stabilizes or probably it actually starts increasing. Okay, and so the point where you stop your fit, your best fit is going to be here. The red vertical line corresponds to the minimum of the validation. And in this plot here, I'm plotting actually what I would get without cross-validation, so the blue. So what I would get if I took this point here, okay? While in orange, I'm plotting what I get actually around epoch 200, so the one with cross-validation. So I think luckily in this case, I mean, this is again just a code I write by myself to give examples. Luckily, this is a nice example because it seems that like the one with cross-validation is doing better. But I mean, I think it's just out of luck. Because then I've produced a bunch of these. You see here already it's less evident. So apparently this is the minimum of the validation set, but this is a case that can actually happen, that they look more or less the same. And here again, I'm being lucky. Cross-validation seems nice, okay? And then you keep going. This is again quite nice. So here it's even more evident. Training keeps going down. Validation at some point definitely starts increasing. So you stop, but here, yeah, I mean, that's life here. But still, no cross-validation looks a little bit, looks worse. Yeah, we can all agree, right? Fine, here another example, and then then actually it can happen also in real life that for some weird reason, actually the validation is lower than the training. I mean, everything can happen. Then you can try to make sense of it, but, and is this wrong? No, it just means that for that specific fluctuation, you're being very lucky or unlucky, depending. I mean, it's not that you can exclude that the validation. I mean, if you see that all of your replicas are doing this, then probably means that the minimizer you're using is kind of crap, right? Because even if it's fully minimizing one function, it's not able to get it lower than another one, which is randomly falling. Okay, fine. Enough of this. Let's go back for a moment. Yeah. Yeah.
Why is the training not really going down towards zero?
So yeah, this is, so there are well, there are probably, let's say, two reasons. One is that probably one could, in this specific notebook, one could optimize the training much better than what I did. So I didn't optimize it. I just took a random minimizer. I put fixed training length, fixed learning rate, and run it for a bunch. But then also here we are looking at real data. Okay, so real data are actually noisy. So you do not expect that there is actually, of course, there will be always a line which goes through all the points, but you don't know how bad this solution is. Well, I mean, for sure it's wrong, because for sure the thing that goes through the points will be overfitted. But we'll see the next notebook in the context of closure test. There are situations in which you do know that there is a simple solution and you want to find it. But the points when here we are actually using real data are noisy. They're affected by statistical and systematics errors, so they're not drawn from a smooth line. They're a noisy system, and when you do a fit on noisy data, in principle, you do not expect to be able to reach chi-square 0. Actually, you expect 1. So if you're not affected by systematics by unknown systematics, what you would expect from basic statistics is that your chi-square should be order 1. Because basically, this is what you're doing when you're minimizing the chi-square, right? You want your data to be described within the experimental covariance matrix. Yeah, you can always overfit and yeah. Yes, but it would still require some work. And so here I could make the chi-square better by working on the optimizer and so on. But I mean, you know that there is not an underlying simple solution just because we are looking at real data which are noisy. We will see in the next notebook that in the other case, when you do know that there is a simple solution, actually also with a random optimizer like this, you do expect what you're saying. So that the chi-square should go to 0 numerically. So this is, yeah, good point. Now, this is respective to the fluctuated data. So because here which is not what I should be looking at, actually. I should be looking at the one with the real data. But here, so this is because this is the training validation. So I'm using chi-square and loss function just in the same way, but it's wrong. Actually, this is the loss function. So the chi-square is always with respect to the central data, if you want. But here, in order to analyze the training, I'm plotting the loss function, which means that it is computed with respect to the actual replicas that are going into the training. But at the end, when you want to, let's say, assess the quality of a fit, you have to look at the chi-square with experimental data, of course. Not the chi-square with respect to the specific fluctuation that you have fitted. But in order to do these plots on the other way around, you want to really see the loss. Okay, now a small comment. When I say, so when talking about the training validation split here, I told you that you have to actually mask the covariance matrix. Are you feeling happy with that? Don't you feel some kind of, aren't you uncomfortable? So, yeah, why?
It might not be the case, but
Mm-hmm.
you might still preserve the correlation.
Exactly, that's exactly the point. So exactly. So say, consider point ij. The entry in the entry ij in the covariance matrix is telling you something about the correlation of the points, right? Meaning that if points I, let's say, goes up within its error, point j should go up or down depending on the fact that it's correlated or uncorrelated. Now, so that I and j are one in the training and one in the validation. The poor entry ij in covariance matrix is just killed, and you lost, you're losing this correlation, this information, right? So you're throwing away, in a random way, literally, information that you have no idea how important it is at the end of the day, okay? So it might be a problem. So this is actually wrong, right? So what should you do? Well, yeah, I mean, you could argue. I mean, there is always like you're always asking to the poor experimental people to publish all the information they have about the correlation, then you end up throwing it around. I mean, just throwing away random information. So, can you think about a better way of doing this? So the question is, can you do a sort of training validation split without throwing away correlation? Or maybe no. I mean, life life can be crap, right?
You may filter out the entries of the covariance matrix that are really small and you can find the corresponding data points. And then
So say it again.
could you find like entries of the covariance matrix that are really small, so like that would correspond to points that are not correlated at all?
Okay, but say that you actually want to do this. How would you do that? So let's say that you want to find out the ingredients that are actually having the components that are weighting more in your loss function, your chi-square, which is kind of what you're saying. How would you do that? Consider that you have thousands of data, so scanning, well, okay, of course you could do this with a piece of code, but so you should just change basis. You should put yourself in a basis where the correlations are evident, which means what? What's a matrix? What's the form of a matrix where the correlations are just, where there are no, how's a matrix without correlation? A diagonal matrix, exactly. So, exactly. So you should work in the basis which makes your experimental covariance matrix diagonal. Okay. So basically, you can rewrite this thing, let's say, in this way. Well, okay, whatever. This is now diagonal, and this U is basically, yeah, you're putting yourself in a different basis, and then you do the training validation split in this space, so on the entries of this vector. Okay, so each one of these, the components of these vectors are basically a linear combination of data that they have no physical meaning, but you don't care. You just throw away. I mean, you put half of the entries of this vector in your validation set, half on the test set, and in this way, you're sure that validation and test are, there is no correlation between them, okay? And this is actually the way in which you should do this, okay? Yeah, this is the way that you, yeah, of course, you could, well, what do you mean? You mm-hmm, yeah. Mm-hmm. Yes. Yeah.
You go back to a situation where you have only
Yes. Yes.
this useful also independent of the any validation.
This you can do always, but at the end of the day, you're minimizing a function of theta, right? So if your minimizer it's doing its job, it doesn't care in the way in which the final result is obtained. So you can still rewrite it like this, but then your minimizer is gonna see this anyway, right? So, but still you could do this, for example, as you were saying, to actually find out which are the block which are kind of which have more weights in the chi-square, right? You just look at the sides of the eigenvalues of, and you can determine kind of linear combination of data that are actually 90% of your chi-square if you want.
So now I'm thinking that it is not guaranteed that you can have validation, right?
Well, okay, that's that. I was gonna ask that. Should you? I mean, well, so an experimental covariance matrix is a covariance matrix. In principle, should be positive definite. In principle. But then when your code crash and you find some warning that contains the Cholesky word in it, you know that you're trying to invert a matrix which is not positive definite. But then usually you find out which data set is causing this. And then there's nothing you can do. You just write to some busy experimental person who will not reply to you, saying, hey, your covariance matrix has problems. I mean, in principle, a covariance matrix should be
If there is a full correlation.
no, okay, sorry, still blocks. For sure, block diagonal. Yeah. Block diagonal. But also block diagonal. It's I mean the problem is that very often you have like if you try to the diagonalize or block diagonalize it, you get 10 to the minus 16 at some point on the diagonal, right? But which means that no one has done the most stupid check on the matrix that is being delivered. So, but okay, so this is the, so if you have full correlation, you know that you cannot do training validation split just again in a random way also in this basis. There are blocks that should go either full in training or full in validation. Yeah. Or you can try to minimize the amount of information that you lose, but at least you're doing it in a kind of way that you know what you're doing. So do you want to stop 10, 5 minutes, something, and then we, okay. So okay, in the last 30 minutes, we are going to say something about how we can validate the methodology. So what does it mean to validate? So we have built all this machinery, but then actually would like to have some quantitative way, which makes kind of sense from a statistical point of view, to actually say we trust our results in terms of central values and uncertainty. Okay, so meaning that we are kind of confident in delivering a set of PDFs that people are going to use to do their own studies. So there is a lot of work actually in this direction, and all of this goes under the name of validation of the methodology. So here I'm giving some references when you can find more about this. And I think that the only thing we will look at in the notebook, there is something more, but I think the thing that we will discuss now are closure tests. So what are closure tests? The idea is that, so far we were looking at the real data. So the data that you were loading were taken by HEP data, so they were the official data from BCDMS. But one way to see if we are actually doing something meaningful is to, rather than starting from real data, we could start from kind of synthetic data, pseudo data that we build using an input PDF that we know. So we build this synthetic data, we fit them using our methodology, and then we check that what we get at the PDF level is actually compatible with the input law that we have taken in the first place. Okay, so it's quite simple. I mean, this is the idea. You produce data knowing the answer, and you check that your methodology is able to reconstruct the answer within the error. Okay, and this is what we're going to try to do now. So if you look at the notebook, again, you have first you clone the same stuff as before, you load the same ingredients, and then there is again the code we are defined before for the neural network. So these cells are just exactly the same, the chi-square, this function to perform the fit of a single replica. So you don't have to look at the code. This, I mean, if you call this function and you give this input, so central values, experimental covariance matrix, the number of epoch you wanna use, the FK table, noise tells you whether or not you want to apply this, you want to propagate the error. So of course, usually will be, well, no, it depends on what you wanna do, but it can be either true or false. And training validation split if you want to implement training validation split or not. So this is the solution of the previous exercise if you want. And the first thing that we're going to do is a level 0 closure test. So what's a level 0? So there are, when talking about closure test, there are 3 possibilities, level 0, level 1, and level 2. So level 0, basically it means, let's assume that we have, well, it's the simplest thing you can think about. So your data are gonna, you produce your data just taking the FK table and multiplying it by the reference PDF we are choosing. So this is now our input PDF, the answer to the problem. We produce central values for the data just in this way. Okay, so this is like a smooth function. A very simple and smooth function is the black line I was plotting in all the plots. So the data you're gonna get are very clean. I mean, there are no systematic shifts or anything like that. So in a level 0 closure test, you just basically run your code, your minimizer, on this kind of data forever. Okay, so if you run forever on perfectly smooth data, what do you expect to reconstruct at the end? You should reproduce exactly that, at least in that region. So if you're, and the chi-square should go to 0. In this case, I mean, the chi-square in principle should always be able to go to 0 if your functional form is flexible enough. But in this case, it should be simple, right? Because it's not a noisy, the data are not real noisy data. The data are perfect, are just coming from a very simple function. So everything is smooth. So you should see, so if you run your minimizer for 500 epoch without stopping or anything, you should see 2 things. At the level of the chi-square should go numerically to 0. And at the level of the function, you should get a very good reconstruction of this guy. Okay, so this is the simplest test that you can do. Okay, so the first exercise is to do this. So in practice, it should be quite simple, meaning that, or maybe not, I don't know, but you can basically take the same code from the previous notebook. But now what do you have to do? The central value is not going to be anymore the value that you load in the upper cell. It's not data anymore, but you have to build your central value like the first exercise of the first notebook. So you do this. So you do your level 0 data are going to be equal to FK, and then you can use the hat F, where F is this guy. Okay, so you define this variable and you throw it in the fit replica function here, and you do the same training loop as before. Actually, maybe I can, so no, these are the solutions. Spoiler. So, okay, I will also put the solutions of exercise 4. Exercise 4 was about performing the Monte Carlo fit before, okay? So I'm putting it now in the notebook 1, if I can find it, which is here. Oh no, it's already there. No, it's solution. Solution, solution, solution. So in notebook 1, I'm putting now the solution to the exercise where you have to perform the fit with the replicas. So basically, you can use that piece of code, this. So I'm saving it. So now you should be able to see it as well. The fit replica function, you can use the one which is already in notebook 2, is already there. What you can take from this piece of code is actually this loop here, which is the loop where you see the fit replica function is called 10 times. This should take, I don't know, 3 minutes, 2-3 minutes to run this thing. So you can take this, you put it in the, well, this, maybe. You put it in the new notebook, check that probably the fit replica that you have in the notebook takes a slightly different input, but I mean the concept is the same. And then you do the same for 10 times, but this time you're fitting 10 times exactly the same perfect data, and you see what you get. So you could say, well, why should I fit 10 times the same thing? I will get 10 times the same thing. Well, check. Okay, is it clear? Okay, let's, yeah. 5-10 minutes, and then we discuss the solution. Has anyone managed to produce something? Kind of. Okay, let's discuss 5 minutes the solution of this, and then I will leave. Then we discuss the following points that we have still 10 minutes to try to do it and to look at the solutions quickly. So here there's the code. You see, it's the same code I copy. Just a second ago, right? But yeah, generate episode data using for point node, which is just our reference PTF, and the FK table. So YL0 is our level 0 data. And then you see in this loop, I'm plotting 5 replicas, training them for 500 epochs. And at this point, you see there is no training validation, just because here I'm really testing the simplest possible thing. I'm just training for a long amount to death. Okay, I just want to get 0 chi-square. Okay, on perfect data. I wanna see what I get. So training validation is false, and also noise. This was activating the replicas fluctuation is false. So I'm fitting 5 times exactly the same thing, and then I'm plotting the results. So, yeah, what do you say? What would you say? I'm reconstructing the thing exactly, but am I getting the same result? No. I mean, you're still able to see that there are different lines. So even though I'm doing exactly the same thing 5 times on exactly the same data, I mean, of course, here basically you cannot distinguish the different lines, but here, yes. So the solutions I'm finding are actually different. Do you expect this or not? Hmm? The epochs are the same. I'm training them, all of them, for 500 epochs without training validation split. So the point is that the yeah.
Because we have the real data in the right part of the graph.
Sorry, we have say it again.
Data taken by the experiment, the BCDLS,
Mm-hmm.
and we have no data on that part because we used only a small part of the data.
No,
Like yesterday.
the data are, I'm generating values for those data, for exactly those 248 data, using an input PDF and using the FK table. And then I'm refitting them using the same FK table. Okay, so but the data, I mean, the kinematic coverage, I mean, the data are exactly the same as yesterday. I'm just substituting the real central value with a fixed central value that I put there, which has been constructed using a specific input. And here I'm checking if I'm getting exactly the same input. I mean, if I can reconstruct this input exactly. And I was saying that it looks that you can, but still if you run the code 5 times, you get different answers somehow. So they all look reasonable, right? Meaning that in the region where you do have data, you cannot distinguish one from the other. But then I was saying, well, but in the region where you actually don't have data, you can still see a difference, which is telling you that it's a different solutions I'm looking at, right? Even if you have run 5 times the same code. So the point is that you're still exploring a space which is 700 dimensional, I don't know what. So it's not that you're ending up in the same exact minimum. Okay, there is a population of minimum. All of them here have chi-square, I guess, quite low, but they're just different. So the final result will depend on where you start in the parameter space. I mean, every time the network is initialized randomly, and so you start from a different point, and so you will end up in a minimum that is probably equally good, but different. Okay. Well, exactly. I mean, if we zoomed here, we would probably see. Yeah. Yeah, so if you convolute each of these with the FK table and you look at what you get, you should get something which is numerically basically the same. But at the level of the PDF, the network you're learning are actually a bit different. But so you can also think about, so what's the error that you're finding here? The error that you're finding here, if you want, is you can try to quantify it, and it corresponds to the error that you will do in any case, which is just due to the reconstruction. You are trying to determine a continuous function from 200 data. This is not possible, okay? There is not a unique answer. So there is a reconstruction error, which is just inside the problem itself by the way in which the problem is defined. So you do expect an error here, okay? And I mean, if you can do this exercise with the real data, with the full network, and you would see that it's actually much bigger than this. And that error, so the spread of the replicas at this point, just represent the error connected to your inverse problem. So to the fact that you're trying to reconstruct a continuous function from a finite amount of data. Okay. Now we can look at the chi-square. So these are the chi-square of the 5 replicas. And you see the y-axis now is logarithmic. So you see that they're all going numerically to 0. So here it's 10 to the minus 5. If you remember the plots from the previous notebook, they were going to 0.1 or something, okay? So here it's going numerically to 0, but you see they are different. So here I'm in different places in the space of parameters. So again, I'm getting different answers, but all of them, for all of them, the chi-square is going to 0, okay? I mean, these weird fluctuations, I don't know what's happening here, but numerically they're going to 10 to the minus something. Okay, so basically, and this is what you want to see in order to validate your minimizer. Okay, so you use level 0 closure test basically to assess the goodness of your minimizers and of your methodology in the simplest unrealistic scenario in which you have data which are perfect. Okay. Sorry, say it again? We are saving, so in order to produce this plot, for the plot before. The plot before corresponds to this epoch. Okay, so here I'm not doing training validation set, training validation split. Is this what you're asking?
Yes. No, because I think that the shift could be also
What do you mean the real minimum?
the real minimum, for example,
You mean here rather than this one? Yes. Okay, yeah, okay, fine. Yeah, I mean, it's in log scale, so, but, no, here I'm just plotting these. But you see that also if I look at the real minimum, I mean, the real minimum of the blue line is this one, which is anyway different from the real minimum of the, but okay, in this case, I'm just, the approach is that just train as long as you want and look at what you get at the end. Okay? Good. The next step is level 1. So what's level 1? So what can you do in order to make these tests more realistic? So the idea is that basically you can add, so experimental data are noisy, okay? They're not coming from a smooth underlying PDF. If they are, they're still affected by statistical fluctuation, by systematics, and so on. So what you want to mimic in these validation tests is whether or not your methodology is actually able to deal with noisy data. So when we talk about level 1 closure test, basically we do the same as in a level 0, but this time we add a fluctuation. So level 1 will be built like this, but then we add some epsilon, where epsilon is a constant shift, which is just drawn by a distribution centered in 0 and having as a Gaussian distribution centered in 0 and having as covariance the experimental covariance matrix. So basically you're adding, if you want, a systematics to the central value of data points, which is compatible with the experimental error. Okay, so you're adding a little bit of noise in your data, but in a systematic way, meaning that this is going to be your new central value. Okay, so then you can do an intermediate exercise that is, you repeat what's done for the level 0, but this time on a level 1. And what do you expect now? Do you expect to be able to reconstruct exactly the underlying law or not? No, or if yes, you should actually do some work on your methodology. I mean, you do not expect to be so easy to reconstruct the underlying law, just because now the data are not perfect anymore. So, okay, there are 5 minutes left, so just look at the solutions. So if I do the same, this is what I get. And you see that it's actually very similar to what we were getting when we were fitting the central value of the experimental data, right? This is what we are mimicking here. We are mimicking, I'm not sure if it is English, but okay. This is what we are pretending to be doing. Like fitting the central value of true experimental data, which means data that are probably, hopefully, coming from some underlying law, but which then are affected by some shift, which we are assuming is compatible with the error which is quoted by the experimentalists. Okay? So this is an intermediate step. And the chi-square at this point, you see, we get back something which, again, is similar. Here we are again in log scale. Here there is 1. You see, we are slightly below 1. So again, at the chi-square, we are getting back what we were seeing in the first notebook when fitting the central value. Something which is order 1, a little bit less. Okay? But then in order to kind of test the full methodology, we are level 2, which means that we fit this, but in a Monte Carlo approach. So here, these replicas are produced, you see noise false, and training validation false as well. So we are fitting 10 times, 5 times, no, 10 times the same noisy data. To complete the picture, we fit the noisy data, but this time with the full approach, which means that in a level 2, we do exactly as we did the Monte Carlo fit in the first notebook, but having these in the place of the central values, and also generating replicas to propagate the experimental error. Okay. And what do we want to see? We want to see that we get something which looks like this. So basically, the underlying law, which is the one we started from, is reconstructing within the error. But again, qualitatively, this plot looks very similar to what we get at the end of notebook 1, where we were fitting real noisy data from BCDMS, propagating the error. Okay. So, well, okay, this was the solution. You're right, I forgot. No, I was thinking to run it in the break, I completely forgot. No, this is the solution, because this takes like 3 minutes, which is fast, but then if I have to stop for 3 minutes, it's kind of awkward. But I can rerun it for you in a second. Cool. Few words. So there is a second part of the notebook that we are not going to see. So all of this is very qualitative. So I've spoken a lot, I've waved my hand, but I mean, there are no numbers. So if you want to convince a referee that this is good, you actually need to produce numbers. So there are then ways to actually to turn this kind of qualitative arguments into numbers and plots, which have some sense on a statistical point of view. And this is the way in which you test whether or not your methodology is faithful, meaning whether or not you're able to describe data which do not enter your analysis in the first place within the error you quote at the end. So the aim of the game at the end of a validation procedure is to prove in a way which is statistically solid that you are able to describe data points about which your fit doesn't know anything within the theoretical error you quote at the end. Well, by theoretical error, I mean the error with the PDF. So you have DIS, you fit all DIS data, you produce a PDF set with a certain error, then you take this PDF set and you compute theory prediction for Drelian, which was not included in your fit. Your methodology is faithful if data for Drelian are described, are consistent with the theory prediction within the theoretical error that you're quoting, not within the experimental error. Okay, and there are a bunch of tools to do this, but yeah, we don't really have time, so I will upload all the notebooks. If you're interested, you can have a look. And if you're interested even more, actually, you can check if you have GitHub. You open GitHub. This is my GitHub. Well, first of all, you will find on this page here, you will find the links to these notebooks. But then you can actually, if you write an PDF, you will have access to this repo. Is public, and this contains the real code. Okay, the real fitting code. Okay, which I wrote this tutorial just kind of taking inspiration from what happens here. This is the real thing. You can try to download it, to play with it, and so on and so forth. There is the documentation is there is a documentation, so you can read this, play with it if you're interested. If not, please don't. and yeah, everything is public. So yeah, if you're interested in these kind of topics, if you look in the main repo, you will find also different codes. Like Echo is the one taking care basically of producing, well, not really, but producing what is needed. Well, Echo computes the evolution of the PDF, and then it recasts it in a way that then can be implemented in the FK table. So there is a whole pipeline of different codes that are used to cover the different aspects that we have seen in these tutorials, and everything is public and developed as an open source framework. So if you're interested or if you need this kind of stuff for your research, you can find everything online on GitHub. Cool, and with this, I think I'm done. So have fun for the rest of the school.